Imagine proving you know a password without ever saying the password. That sounds impossible, but it is the core idea behind one of the most powerful tools in modern cryptography. Most of the time, proving something means revealing evidence. If you prove your age, you show an ID. If you prove you paid, you show a receipt. Zero-knowledge proofs ask a different question. Can you prove a claim is true while revealing nothing else? A zero-knowledge proof has two main roles. The prover is the person or computer trying to prove something. The verifier is the person or computer checking the proof. The prover wants to convince the verifier, but without handing over the secret behind the claim. The promise is simple to say. I can convince you that I know something, or that I did a calculation correctly, without showing you the hidden information used to make it true. Here is the classic intuition. Picture a cave shaped like a loop, with two paths leading to a locked door in the middle. Alice knows the secret word that opens the door. Bob wants proof that she knows it, but Alice does not want to tell him the word. Alice walks into the cave and chooses one side. Bob cannot see which side she picked. Then Bob randomly asks her to come out from the left path or the right path. If Alice knows the secret word, she can open the middle door and come out wherever Bob asks. If Alice does not know the word, she might still get lucky. She could enter one side, and Bob might ask for that same side. So one successful round does not prove much. But if they repeat the challenge many times, luck becomes a very bad strategy. Every round gives Bob more confidence. Alice keeps answering random challenges correctly. Bob learns that she can control the outcome, but he still never hears the secret word. The proof grows stronger, while the secret stays hidden. Cryptographers usually describe this with three ideas. If the claim is true, an honest prover should pass. If the claim is false, a cheater should almost never pass. And if the claim is true, the verifier should learn nothing except that truth. The first idea is completeness. If Alice really knows the secret and everyone follows the rules, Bob should accept the proof. A good proof system should not punish honest people for having the right answer. The second idea is soundness. If Alice does not know the secret, she should not be able to fool Bob except with tiny probability. This is what makes the proof meaningful. It is not just a performance, it is a test that cheating cannot reliably beat. The third idea is the special one. Bob should gain no useful knowledge about the secret itself. He becomes convinced that Alice knows the secret, but he does not become any closer to knowing it himself. If this kind of explanation helps make cryptography feel less mysterious, consider subscribing. We are going to keep building the idea step by step, because zero knowledge sounds like magic until the pattern becomes familiar. Now imagine a completed Sudoku puzzle. You want to prove that you solved it correctly, but you do not want to reveal the solution. A zero-knowledge style approach can let someone check that the rules are satisfied without seeing every number. The verifier does not need the whole hidden solution. They only need confidence that each row, column, and box follows the rules. The clever part is designing a process where the verifier can test correctness without collecting the actual answer. Real zero-knowledge proofs do not rely on cave walls or paper puzzles. They turn a claim into a mathematical statement. Then they create a proof that the statement is true, while hiding the private inputs that made it true. The private input is sometimes called a witness. It is the secret information that makes the claim true. The public claim might be that a password hash matches, an account has enough funds, or a calculation was done correctly. Think about logging in. A website should not need to store your real password in plain text. In a similar spirit, zero-knowledge thinking separates proving from revealing. The goal is to verify a relationship without exposing the sensitive value inside it. Privacy is the obvious use case, but it is not the only one. Zero-knowledge proofs can also help with verification. They can let a small proof stand in for a large computation, so someone can check a result without redoing all the work. The cave story is interactive. Bob asks random questions and Alice responds. Many modern systems use non-interactive proofs instead. The prover creates one proof, and anyone with the right public information can verify it later. On the internet, people and machines often do not trust each other. We want access control, payments, identity checks, and audits, but we also want less data exposure. Zero-knowledge proofs help because they reduce the need to share raw information. A simple identity example is age verification. A service may only need to know that you are over a required age. It does not need your full birthday, home address, document number, or every detail printed on an ID card. This idea is called selective disclosure. Instead of showing an entire credential, you prove only the fact that matters. The verifier gets a yes or no answer to a specific question, and the rest of your personal data can stay private. Blockchains are public verification machines. They let many strangers agree on a shared state. But public verification can clash with privacy because public networks often expose transaction data. Zero-knowledge proofs offer a way to verify rules without revealing every underlying detail. In a private transaction system, a proof might show that a payment follows the rules. It can show that the sender had the right to spend, that no coins were created from nothing, and that balances still add up, without revealing all private transaction details. Zero-knowledge proofs can also help with scaling. Instead of putting every small computation directly on a base blockchain, another system can process many operations elsewhere and post a proof that the final update was valid. This is often called a validity proof. The blockchain does not blindly trust the off-chain system. It checks the proof. If the proof is valid, the chain can accept the result with much less work than repeating every step itself. You may hear names like SNARKs and STARKs. These are families of proof systems with different trade-offs. Some focus on very small proofs. Some focus on transparency or different security assumptions. The names are less important than the idea behind them. Zero-knowledge proofs are powerful, but they are not free. Creating proofs can require serious computation. Some systems need careful setup. Proof systems are complex, and the stakes in circuits, assumptions, or implementation can create real security problems. To make a proof, developers usually express a claim as a circuit or a set of constraints. That means they translate a normal question into a form the proof system can understand. This translation step is one of the hardest parts of building real applications. A proof only proves what was written into the statement. If the statement is incomplete, the proof may be perfectly valid, but still not mean what people assume. Good zero-knowledge design starts with asking exactly what needs to be proven. This is a common misunderstanding. Zero-knowledge proofs do not magically prove that a real-world claim is true. They prove a mathematical statement about data. If the input data is wrong, fake, or poorly connected to reality, the proof cannot fix that by itself. Zero-knowledge is also not the same thing as encryption. Encryption hides a message so someone with the right key can read it later. A zero-knowledge proof convinces someone that a statement is true without giving them the hidden data to read. Another misunderstanding is that zero-knowledge automatically hides everything. A proof can hide the secret inside a statement, but the surrounding system may still leak metadata. Timing, network addresses, account patterns, or repeated behavior can reveal information if the whole design is not private. The deeper idea is data minimization. In the physical world, we often reveal far more than needed. Online, that habit became normal. Zero-knowledge proofs point towards systems where verification does not require constant exposure. This could matter for identity, finance, audits, access control, voting systems, machine learning, and many other areas where people need proof but not full disclosure. The technology does not remove trust entirely, but it can move trust away from raw data sharing. So the simplest version is this. A zero-knowledge proof lets a prover convince a verifier that a statement is true while revealing nothing beyond that truth. It is a way to separate confidence from exposure. That separation is why the idea feels so futuristic. The internet has spent decades asking people to prove themselves by handing over data. Zero-knowledge suggests a different pattern. Prove the fact, keep the secret. If you have a question about zero-knowledge proofs, leave it in the comments. And if you want the next explainer to go deeper, suggest a topic like ZK rollups, digital identity, SNARKs, STARKs, or privacy coins.